So, hi, my name is Paige Dinh, and my mentors were Diana and Marliana. And my field of research was geo and astroscience. So, my research topic specifically was tracing the impact of coronal mass ejections on power grid failure, specifically following the Hydro-Quebec event of 1989. So, in this, we're going to go over how a solar eruption evolved into a power grid collapse during the March 13th, 1989 Hydro-Quebec blackout. And as the name suggests, the Hydro-Quebec blackout was the largest solar-induced power disturbance in North America, which left 6 million people without power for 9 hours. So here, I'm going to trace how a full chain of how it happens. So a CME, which is a coronal mass ejection, we'll go over that in a second, leaves the sun and it couples with the Earth's magnetosphere. Then it induces ground electric fields and drives GICs in long transmission lines. To do this research, I used a social approach with archive indices and model disturbance footprints. Then I aligned those with reported grid events. So the practical outcome of this would be a set of benchmarks for forecasting, engineering protections, and future prevention. So before diving further, let's go over a few key terms. The first one is CME, which you'll hear me reference a lot throughout this presentation, is a burst of solar plasma and magnetic field released into space. The IMF, or the interplanetary magnetic field, is a solar field embedded in the solar wind. And if you look one down, the southward IMF, or the BZ component, um, is when it points southward, and it's when the Earth's field is the strongest. The dB over dt means the rate of change of the magnetic fields, and it states a high value strive induction. Geomagnetically induced currents, or GICs, are the actual like unwanted currents flowing in long conductors like power lines. Um, And to monitor activity, we use indices. So the AE index captures the auroral electrojet strength and substorm intensity, while the DST index measures how depressed Earth's ring current is. So that represents the global storm strength. So for slide three, my guiding questions were first, why the storm produced a system-wide collapse. Second, which space conditions, especially the orientation and persistence of the IMF-BZ, maximized energy transfer. And third, how the disturbance footprint's size and position increased exposure. I also considered the Canadian shield's high resistance, the long HV lines, and the limited 1989 era mitigation, as there was not the same level of technology we have now. And finally, I tested timing. So did the AE and DST peaks line up with the alarms of the 7:45 blackout? So in this project, I combined multiple data streams to trace the chain from the sun to the Hydro-Quebec blackout. I used solar papers on active region magnetic complexity. This kind of explained why the eruption was primed while geomagnetic magnetic indices like DST and ASE showed storm strength and substorm activity. I try to align these indices with the historical grid reports to find when the strongest AE peaked. So it was our best proxy for like intense, rapidly changing um, ionospheric currents. I also tried to make sure that or reference if they coincided with the alarms around the 7:45 collapse. And then I used blackout simulators, modeled substorm footprints as like the spatial analogs. So with that, I was able to reason about how broad areas of high disturbance could like simultaneously stress like long transmission lines. And the final step was grounding in Canadian shield geology, where high resistance forces currents into grid infrastructure rather than just like dissipating to the earth. So combine these methods, link solar eruption conditions and geomagnetic stress windows, and also the spatial disturbance spread and the ground coupling into a single causal like story for the Hydro-Quebec event. So while the footprint of the maps are modeled and historical records have uncertainties, if you combine them together, they can create a stronger, more solidified case that sustained substorms and high DBDT directly. The fact that sustained substorms and the fact that DBDT directly led to transformer saturation and voltage collapse. So here's our first figure. Um, this figure shows the CME that triggered the 1989 blackout. It erupted from the sun and traveled through space before striking Earth on March 13th. And when the shock front arrived, it compressed the solar wind and then disturbed the magnetosphere, where the southward BZ directed the magnetic field which enabled a strong coupling with Earth's field. And this like transfer of energy fueled the like intense geomagnetic storm that ultimately drove the geomagnetically induced currents that into Hydro-Quebec's network and set the stage for the blackout. So next up, this is our second figure. Figure two shows modeled substorms cases number 12, which is A, number 28, which is B, and number 41, which is C. The blue areas marked where the GIC surpassed high impact thresholds. So from panel A to panel C, the footprint expands, which means more of the grid is exposed at once. So morphology matters because a wider, better placed footprint can be more dangerous than a narrow, intense one. So although these maps are drawn over Europe, the substorm behavior is like indexed from the 1989 March 1989 event. So if we apply that morphology over Quebec and the northern United States, we see how many assets might be like stressed at the same time. And this is like invaluable for exposure mapping and contingency planning. So next up, we have figure three, which plots the AE index across March 12th through the 15th. The blue curve shows the auroral electrojet intensity, and the green vertical lines are the SCs, which are the abrupt increases in the geomagnetic field caused by solar wind pressure changes. So these event markers represent the Hydro-Quebec failure and later the UK transformer alarms. And you can see the AE peaks clustering near these events because AE spikes correspond to rapid changes in the ionospheric currents. They're pretty strong indicators of high DBDT on the ground. The timing alignment supports a causal chain, and it isn't random. So in practice, AE these AE can be used as operational threshold and provide an early warning signal to prompt like grid operators into better readiness. Just to add, large negative DST values indicate stronger storms, and then higher AE values typically mean stronger and more dynamic auroral activity. And for our last figure, figure four captures the pre-eruption solar magnetic environment. So if you can see, panel A shows free magnetic energy rising in the days before the event. And then panel B shows the energy ratios evolving, which reflects like a changing field and configuration. Panel C is a magnetogram highlighting complex polarity patterns, which is a little bit harder to articulate in um, 10 minutes. But panels D and E basically show the decay index versus the height approaching the instability threshold. So these conditions that are conditions that can permit an eruption. In the Halley scheme, the alpha is the simplest, so progressing through the beta and gamma into the beta gamma delta as the most complex. Greater complexity correlates with higher eruptive potential, which becomes geoeffective when the IMF-BZ turns southward at Earth. So remember, this is the strongest current. Okay, next up, the Hydro-Quebec blackout remains a defining case because it put a concrete economic price and tag on space weather. So hundreds of millions in direct losses and billions when ripple effects are considered because nobody in Quebec or in the northern United States had access to any sort of power for 9 hours. So economic modeling emphasizes that utilities in high latitude regions with longer transmission lines, so like phone poles and such, were at risk, and resistance modeling using GIC simulations help identify these vulnerabilities. So comparing across these events, the 1989 blackout shows how grid collapse can cascade quickly into like a vulnerable region, while the 2003 Halloween storms revealed more global but less catastrophic events. So airlines and satellites were stressed, but power grids mostly held. The Carrington event, which was an event held back in the that happened back in the 1800s, provides the ultimate reference point, showing that storms over a magnitude larger are physically possible and would dwarf both the 1989 and the 2003 in scope. So together, these comparisons kind of highlight why the resilience investments today, like transformer hardening and improved grounding, are like economically justified as preventive measures and economically viable. So the main takeaway from this research is that solar eruptions, specifically coronal mass ejections, have a direct chain of influence over our critical infrastructure, especially now when technology is used in every aspect of life. So the 1998 hydrocarbon blackout is like a clear case study where the space weather cascaded into like a real world consequence. Um, a geomagnetic storm coincided almost perfectly with grid collapse. And with the unique geology of the Canadian Shield, it had high resistance amplified. The fact that it had a high resistance amplified the problem by forcing currents into the power system instead of like letting it dissipate naturally. And by aligning these geomagnetic indices with the blackout timeline, we kind of see how these substorms put enormous stress on the grid. So while these events don't really happen every day, the magnitude of their impact means they deserve like serious attention. So this case kind of proves that like natural space weather processes can threaten national infrastructure in a way similar to cyber attacks or natural disasters. So looking forward, the question really isn't if another major geomagnetic storm will hit Earth, but when. So this makes preventative measures critical. So one step is real-time monitoring power grids. We need to incorporate CME forecasts and geomag indices like the DST into AE in their operations. This would allow utilities to take protective action hours in advance. Hardware changes like transformer designs that could withstand GICs are another line of defense. And beyond engineering, policy also matters. So mapping vulnerabilities based on the regional geology can help prioritize upgrades, especially for lower income areas. And international collaboration is essential because CMEs affect multiple countries at once. And finally, public preparedness is key. So if governments treat a severe space weather as a natural hazard, similar to earthquakes or hurricanes, we can be more resilient when the next major storm strikes. And that is all. So thank you to Talaria for giving me this opportunity for to research such an uncommon, I feel, topic, and to my mentors who helped guide me through this whole process. Any questions?